electric field with a tiny hole, electric field. The electric field is negatively charged, so this positively charged chlorine I'm now going to represent with a sphere and a positive charge. It goes to the electric field, and the electric field accelerates the ion. So step 2, the negative electric field accelerates the positive ions and makes them into a beam. Now the tube which it's going to accelerate through to get to the detector is curved for a specific reason. Which is related to step 3. So far we have step 1, which was ionization. Step 2, which was acceleration. Step 4, which was the detector. So the particle shoots out and will curve and make its way to the detector. The curvature of the flight of path is due to a magnetic field. So at the curved point we have a magnetic field. So far we have an electric field and a magnetic field. The electric field was to accelerate the positively charged ion through the flight tube. This is referred to as the flight tube. The magnetic field through this curved flight tube, its purpose is to deflect the positive ion. These positively charged ions will be attracting and repelling to magnetic fields. Now step 3 is deflection. What is deflection? The beam of positive ions is deflected by a strong magnetic field. So we have the magnetic field, and the ion travels through. Now let's say that the chlorine, green chlorine that we have here is chlorine 37, so it has a mass of 37. And let's say we also formed a chlorine particle with a positive charge that was in the sample, and that has a mass of 35. Alright, because we've got chlorine 35 and chlorine 37. So we have two particles on this flight tube. We have a heavy one and a lighter one. The green is heavier. The deflection which occurs, because this is a magnetic field, it's going to be pulling and pushing on these charged ions, and therefore deflecting the direction from the straight fly-off path. Because these are positively charged ions and there is a magnetic field, the degree of deflection depends on the mass to charge ratio, which is represented as the m/z ratio. So if we assume for these two particles they both formed positive 1, that means z is equal to 1, and the mass for one of them is 37, the mass for the other is 35 over 1. So we have mz37 and mz35. The smaller ratio, which would be in this scenario the lighter atom, the smaller ratio, the larger the deflection. So the smaller ratio in this scenario, because both of the denominators are 1, because we assumed we formed a positive 1 charge, the smaller ratio would be the chlorine 35. Its flight of path would be in this direction. So the deflection is larger. Here is the smaller ion. It is deflected more than the larger green ion due to the difference of mass to charge ratio. And that's how the magnetic field affects the deflection. Now this is important because if this deflection, if this separation of the flight of path of these ions was not happening, then the ions would be hitting the same portion of the detector. So what this detector basically does is the y-axis is the abundance and the x-axis is the mz ratio, m/z, and we have 0 to 100%, let's say 50%. Now the mz ratio, which is the x-axis, let's just separate the graph slightly more. We have chlorine 35 and 37. So here is 35 and here is 37, let's say. Now, when the green chlorine 37 hits the detector at this portion right here, a current is produced because the detector has negatively charged electrons and it's passed onto the positively charged ion, neutralizing the ion, and that potential difference triggers that at 35 there was a trigger. So a peak forms. Now